Hey everyone, welcome to this video on Calculus Part 1 with Rethink Education. We will discuss why calculus came around and then we will learn to differentiate from first principles. So let's get going. Firstly, why do we want to learn to use calculus? Now, you may come across some kind of pompous people who refer to it as the calculus, and they take offense to when you drop the. But for the purpose of this video, and I think it's going to be safe just to use the normal reference of just simply calculus. This is not a branch of maths that should kind of make you quiver in fear, but it does require some good logic and many examples. So I'm afraid you just have to accept that, and once you get the hang of things, you'll realize they really aren't too bad. The whole idea of calculus, and specifically differential calculus, is that if you zoom in on a function, then eventually it will begin to look like a straight line. And that is really nice, as straight lines, as you should know by now, are really nice to work with. They're much nicer than kind of whole curvy, horrible functions. They're good things. So from there, it's pretty simple to calculate the equation of the line once you know the slope. And a tangent, as you should know, is a line that touches a curve at a point but does not intersect that curve. It just skims it. And that's what differentiation does. It aims to find the equation of the tangent to a curve at any point. So the first big thing to remember is this. The derivative of a function at a specific point will give the slope of the tangent to that function at that point. Hold on to that idea, as without it there really is no point to calculus. We aim to find the slope of the tangent. Alright, so let's dive straight in. Let's, for example, take the function f of x. I choose a random f of x, but note that it is smooth. Now, I'm going to refer to that in a slightly colloquial way, but what I mean is that it is continuous, so it's just one long line, and secondly, it doesn't have any kind of kinks in it. To show you what this means, I'm drawing two quick examples. This graph here is not continuous, as there clearly is a break over here, and this graph has a kink in it, so it will break the rules for what we need. The above two graphs will not be differentiable at those 2 points, as we cannot fit a tangent to the graph at the discontinuity or at the kink. So if we go back to our example, this graph f of x is clearly smooth. What we are going to do is take two arbitrary points on the graph and connect them with a straight line. Remember that we're aiming to find the slope of the tangent. So let's say at this point, let's take the first point as A and the second point as B along the x-axis. You should easily know how to map these points to the function and therefore find the f of A point and the f of B point. And we can connect these points and therefore find the slope of this line as rise over run, or change in y over change in x, or delta y over delta x. I'm not sure which terminology you use in school, but they all mean the same thing. So therefore we can get the slope of this line is equal to f of b, the height, minus f of a, divided by the length along the x-axis, which is b minus a. So the question is as follows. Is this line that we have drawn close to the tangent to the graph at x equals a? No, it really isn't, but it's an okay start. Well, we can make it a much better approximation by moving the point b a lot closer to point A. So let's try this. Cool, we go through the same steps as last time, and we can see that we are now getting to a much closer line that's close to the tangent, but we're still not close enough. So, well, what can we do? At this point, I want to take a little bit of a tangent to what we're talking about and discuss a pretty fundamental concept to calculus. It has to do with something called limits. I'm not sure, you might have encountered them in class before, but limits are a really handy tool that essentially allow us to make points get really close to other points, but they never actually reach those points. So the best way to describe this is with an example. If you look at the graph f of x here, you can clearly see that there is a hole at x equals a. If I therefore asked you for the value of f of a, you can tell me it's undefined, as it doesn't exist. However, what a limit allows us to do is get really close to that point and to see what the graph f of x is actually doing. We can therefore ask the limit as x tends to a of f of x and see that it actually evaluates to 2. That is the beauty of limits. While the actual value of f of a does not exist, we still know what the graph does by taking its limits. This becomes really handy when we want to divide something by 0 or let something tend to infinity, as both of the above cannot be physically realized. But with limits as a tool, we can see what happens if we divide something that is really, really close to 0, or we can see what happens if we let something become really, really big. Okay, so that's as far as I'm going to go with limits, but please work through the examples in the cog to get a better grasp of what's going on. So we jump back to our example on differentiation. It is now clear that we are going to use limits to allow b to get really, really close to a, so that this line segment that we are drawing actually becomes the same as the tangent. In order to do this, we use a handy tool of rewriting the point b. If we let b equal a plus h, where h is the difference between a and b, then we get the following graph. So you can see that we've just taken the point A, we've added a certain distance to it to get the point B, and we've called that distance h. Now you can see that we can rewrite the slope as f of a plus h minus f of a over h. Our aim was to move b really close to a, but now all we have to do is simply let h tend to 0. If that happens, the 2 points actually move on top of each other, and we get the slope of the tangent. So to write this out mathematically, we get slope is equal to limit as h tends to 0 of f of a plus h minus f of a divided by h. And that's it. That is differentiation by first principles. This little formula gives you the slope of the tangent to the graph of f of x at the point x equals a. So let's take a quick, simple example to show you how this applies. You simply have to follow the same steps and you will be able to solve for the slope of the tangent to the graph at a specific point. So let's take the graph f of x is equal to 2x squared minus 2. And we want to find the slope of the tangent at x equals 2. So we draw our point 2 on the graph, we make another point that is some distance h away from the point 2, and we construct the line through these points. This line here has the slope f of 2 plus h minus f of 2 divided by h, and then we let h get really, really small, and we see how this line gets closer and closer to the tangent, and eventually as h gets close to 0, we get the actual tangent itself. The tangent therefore has the slope limit of h tends to 0 of f of 2 plus h minus f of 2 divided by h. Now it's just some simple algebra to kind of simplify this expression to get the answer of 8. I've written that derivation out in full, so pause the video and follow the steps if you're unsure how to reach the final value. So the tangent of the graph at this point, x equals 2, has a slope of 8. In other words, for every 1 unit I move along the x-axis, I move 8 units up the y-axis. You may be saying, well, that's great, but why on earth do I want to know how to do that? Well, the answer is quite a long one, and I'm finishing off this video for now, but believe me, it will make your life easier at some point. To get a better understanding, you're going to have to watch the next video and complete the Cogs and Calculus Part 1 and Part 2. So for next time, we will be discussing a rule for making this all easier. It's a nice shortcut that you can learn. And then we're going to run through some practical examples as to why this is such an important technique. But that's all for now. Once again, guys, thanks all for watching, and I'll see you next time. Cheers.